Modern flight simulation requires an enormous volume of dense data to function, but that demand collides with hard physical constraints, VRAM ceilings, and processing bottlenecks. A common assumption is that simply streaming raw, massive blocks of photogrammetry is the answer. That approach forces hardware to load immense, unoptimized files, rapidly exhausting memory. Laminar research recognized this dead end. With X-Plane 12, they are abandoning legacy data containers in favor of rewriting the simulator's entire foundational infrastructure. Understanding this evolution requires looking at the simulator as three dependent layers: a scenery container, a physics engine, and a spatial computing interface. The data container dictates memory availability, which dictates how fast the physics engine can calculate airflow, which determines how accurately the pilot can physically interact with the virtual cockpit. Surviving the next decade of aviation simulation requires engineering an entirely new ecosystem. Applying high-resolution textures over outdated scaffolding will no longer work. We can see the first layer of this ecosystem in this animated diagram. It illustrates a tile-based raster architecture, dividing the legacy globe into a precise, optimized grid. At cruising altitude, an airliner needs broad geographic coherence. The system loads only low-resolution tiles covering a massive radius, keeping memory usage minimal. Drop down for a VFR approach, and the requirement inverts. The system immediately subdivides the local tiles directly beneath the aircraft into dense, high-resolution grids, while the distant terrain remains low-resolution. Modern GPUs are explicitly designed to process this grid-like level of detail swapping. By only loading what is immediately necessary, the simulator prevents VRAM overload. These raster tiles function as deep data containers, carrying stacked layers of metadata to define the simulation environment. A single tile holds elevation geometry, precise land-to-water boundaries, vegetation placement, and specific material properties. This diagram shows how the architecture introduces granular overrides. Third-party developers can isolate a single grid tile containing an airport layout, modify its topographical elevation, and slot it back in. There is no longer a need to replace a massive geographic region simply to correct one tricky ridgeline or a misaligned coastline. Intelligent tile-based data loading resolves the immediate memory bottleneck. It also establishes the precise architectural scaffolding required to support dense data streaming in the future. That memory efficiency frees up processing power for the aircraft itself, driving the reliance on modern Vulkan and Metal rendering APIs. This side-by-side graph tracks millisecond frame times. While raw frames per second matters, the true metric for simulation is frame pacing, the millisecond to millisecond consistency of data delivery. When frame delivery stutters, the aerodynamic perception of mass and speed degrades. Smooth frame pacing is strictly required to maintain the illusion of positive control. With that processing consistency secured, the physics engine can calculate complex variables. Wake turbulence is modeled as a dynamic, moving fluid air mass, rather than a rigid, scripted bump trigger. For rotorcraft, this expanded processing allows for precise ground effect interactions and accurate turbine temperature logic based on engine workload. This exactness extends from external aerodynamics into the internal systems architecture, where mechanical components are heavily interdependent. This schematic of an aircraft's hydraulic and electrical lines reveals how failures cascade. A single malfunctioning node instantly disables connected downstream branches, like multi-hydraulics or power transfer units. Many consumer simulators rely on superficial warning lights that flash on the dash but trigger no structural consequences within the airframe. Cascading systems logic forces the virtual pilot into an authentic workflow. You have to diagnose the remaining capabilities of the aircraft and solve the problem in motion. Realism is defined by the presence of consequences. The aircraft feels alive because a mechanical failure dictates what you are actually capable of doing next. Managing those cascading failures requires an interface built for work. The virtual cockpit must function as an active, operational workspace. Traditional VR flight suffers from intense ergonomic friction. Pilots struggle with a physical disconnect, constantly fumbling blindly between virtual visual controls and real-world desktop hardware. Mixed reality pass-through bridges this divide. It merges the physical and digital environments, pulling the pilot's real hands directly into the simulation. By capturing the physical world, users can operate complex real-world hardware, like radios and throttle quadrants, without breaking their visual immersion in the digital cockpit. X-Plane's integration with OpenXR and spatial computing devices like the Apple Vision Pro pushes this operational realism forward. Advanced hand tracking and precise gesture recognition map the pilot's physical movements directly to the virtual avionics switches. The interface becomes your body. Rendering a mixed reality environment demands intense GPU power. X-Plane mitigates this through techniques like eye-tracked variable rate shading. Variable rate shading dynamically channels processing power exactly where the user is looking, the center of their foveal vision, while dropping the resolution in the periphery to conserve resources. By saving GPU power on the interface, the simulator preserves the overhead necessary to load the dense raster tiles we examined earlier. Removing the ergonomic friction of the interface elevates spatial computing from a visual novelty into an effective, practical method for daily flight operations. This X-ray diagram shows 3 independent layers operating simultaneously. The base tile structure dynamically loads dense geographic geometry. This memory management lets the physics engine calculate fluid aerodynamics smoothly. Finally, this responsive physics model demands a seamless spatial interface for the pilot. These dependencies show that X-Plane is engineering a fully coupled operational environment where every system directly informs the pilot's actions. This scalable architecture raises the operational ceiling for both third-party developers building specific regions and training-minded professionals relying on repeatable mechanical behavior. Laminar research is laying the foundational infrastructure required to make the virtual world indistinguishable from the real-world cockpit.